Hello and welcome to our virtual Lunch and Learn today. We'll be talking about types of precision gearing used in today's automation. My name is Rachel Green. I'm the Digital Communications Specialist here at McNaughton-McKay Electric Company. And presenting for us today is Gary Kuzenkowski, Senior Systems Engineer out of our Madison Heights location. Out in the comment section, ready to answer your questions, is Tom Joy, Systems Engineering Supervisor, also out of Madison Heights. We'll have a Q&A portion at the end for Gary to go over your questions in more depth as well. And we'll be getting started shortly, but we'd like to allow a few moments for attendees to join us. As you come in, let us know where you're joining us from in the comment section. You can view recordings of previous virtual Lunch and Learns on our YouTube channel under the Virtual Lunch and Learn playlist, and we cover a new topic every Wednesday at noon, so be sure to join us on your lunch break. For anyone just joining, welcome to our virtual Lunch and Learn today, types of precision gearing used in today's automation. Hi, Tom Joy, and Tom Nelson. Thanks for joining. For anyone just coming in, feel free to say hi to us over in the comments section. Hi, Utsav. Thanks for joining. Good to see you there. We'll be looking for your questions in that comments section as we go along, while our presenter, Gary Kuzenkowski, discusses how certain gearing stages provide assistance and work with Motion Analyzer and existing technologies to benefit you and your facility. Hi, Leanne. Thanks for tuning in. Our specialist, Tom Joy, is ready to answer your questions as we go along in the comment section, and we will have that Q&A portion at the end for Gary to answer your questions and any follow-up questions you have. Hi, John. Thanks for joining from South Carolina. All right, if you'd like to reach out afterward or if you have further questions for Gary, you can always send us an email address at the macandmaclive@mc-mc.com email address there on the screen. And we'll have that up for you again at the end as well. It looks like we have a number of attendees with us now, so let's go ahead and get started. Gary, I'll pass it over to you.
Thank you. Hi, I'm Gary Kuzenkowski. I'm a senior systems engineer in the Drives Motion Mechanics group within our Madison Heights, Michigan office. Today, I'm going to be discussing types of precision gearing used in today's automation. What I thought I'd do first is step through an agenda of subtopics that I plan on covering. First being a couple of previous YouTube presentations that were done by some coworkers. We'll go through a timeline, a history of gearing with a couple of examples. Also speak about mechanical advantage, how the types of those mechanical advantages can vary your application. The hows and whys of gearing usage. What does it do for me? How does it benefit what I'm working on for an application? Next, we'd speak about planetary gearing in general, how it works. Kind of take an inside view of what a planetary gearbox looks like. Almost last but not, how about product selections changing by different gear ratios? What does that do for me? Does that increase a bill of material cost? Does it decrease it? Do I have to worry about any other engineering selections? So that'll change things as we modify the gear ratio, and I'll explain those too in depth. And then we have an example of how that actually changes the overall outcome in terms of price. So I mentioned some previous Motion Analyzer presentations done. The first one was with a coworker, Gary Smith, back in September of 2020. It was covering Rockwell's cloud-based servo sizing tool called Motion Analyzer. It's a great tool. We all use it just about every day. There's also a desktop model that depending on what product we're using, we may prefer to use. But either way, it's great in the fact that I can enter in information into that software tool. And as you'll see here, it will provide me with information on what the actual application is going to look like for both position, velocity, loads and forces, that sort of thing. As you notice across the top bar, after the custom mechanism and profile editor, it's got a selection for transmission and gearboxes. So we're going to kind of forward to that particular snapshot. And here's where I would add in some transmissions I'm going to talk about a little bit later. Belt drives, chains and sprockets, or just a general spur gear. And then as we would move from left to right across the top using Motion Analyzer Online, you would see also an option to put in standard gearboxes. Some of our Encompass partners are located in those selection boxes, so we won't go into too much of that detail. We don't want to make this a commercial for one versus the other. We want to simply explain what we utilize on a day in and day out basis. The next YouTube presentation that was given was done by a coworker of mine named Nolan Van Wormer, and his subject was Let's Talk About Mechatronics. I bring that up into my presentation because obviously gearboxes are mechanical in nature. If we talk about what the real discussion point or definition of mechatronics, it's a multidisciplinary field of engineering. So I'm bringing in and uniting both mechanical footprint, controls, automation, and safety all into one cohesive system. That's important when it comes to analyzing for reference points such as time being spent, money into the job, and any minimization of risks that could occur. After going through the timeline and the mechanical advantages, we're going to speak about again, the hows and whys of gearing usage, but right now I'm going to flip over to a screenshot I took earlier, and it's got to do with something old and dear to my heart, an old windmill. So my point here is that while back in the day, and they're more prevalent now and they're updated and very much an automation piece, back in the day, people weren't using steel, they were using timber. And making gears out of it. So what was that doing? Basically, it was taking a source of power that was available pretty much across the land in terms of wind and converting that torque generation into a process that they could utilize either with more force or a higher speed. So the gears were changing that windmill speed down below a couple of floors in the windmill to something like, say, maybe milling wheat. So if they might have had a couple of rocks and they had a table, they were crushing that, and those gears were supplying that brute force to that end process instead of having someone else do it manually. Basically, the force of the wind tied to the radius of the windmill blade or fan. Basically, a torque is a force through a distance. So as the windmill blade got longer, that radius would expand. And if the force of the wind got greater, I would have more torque being inputted into the windmill and then being able to be utilized in some manual process. Again, if it's crushing wheat or doing some other process, that's what people did back in the day to help them automate what they needed. As things move along in history, more gearing was actually utilized within everyday items. So you notice the couple of snapshots I have here, a clock and watch movement, very low torque, very intricate types of things, but still high precision required to make sure that that timepiece was on time, was doing what it was supposed to be doing. Then things got, then things got interesting when it came to automobiles. Basically, much higher torques required to be putting the power to the road. But the first automobiles, the Model T, were utilizing planetary gearboxes. This is actually, planetary gearboxes were really invented back in the time of Leonardo da Vinci and for different purposes. Moving along with mechanical advantage, what exactly is this? And there are certain types of it, which I'll go through to give you an idea of why you might use one versus another, what benefits each of them has, that sort of thing. So first one up is a chain drive. Rachel and I were talking just ahead of the presentation about biking. This would be what I'm referring to there. As you can see, the different size gears or sprockets will change the output of your bicycle. If I change gears, I might be pedaling faster and going slower, but I have a higher torque advantage. If I change to a different gear selection, I might have less effort pushing the pedals, but I'm going to go faster. So the gear selector and sprockets will change the output of what my bicycle would do. Same thing with a motorcycle. If I go ahead and click further, belt drives are used more in today's automobiles because literally if the belt were to break, there's not as much damage within the engine compartment. However, it's the same principle. I've got a pulley with teeth on it. I have certain diameter of those rotating components, and that is what transmits the torque from one smaller sprocket, say, to a larger sprocket. Last but not least, we have direct gear interaction. So this is a picture of a spur gear, and we're going to talk more about that as it pertains to planetary gearing. So you can see the gears are actually meshing together. They're not separated by some belt or chain. Direct connection is great. Gears need to be hardened to a certain specification. And literally most of the planetary gearboxes in use today have specifications that make sure they're not going to be dysfunctional at a sooner point than later. Going through some of the gear designs. So upper left-hand corner are spur and helical gears. Sometimes those are referred to as offset or parallel. As you can see on the left-hand side, there's one input to a larger gear that then spins with a smaller shaft, a larger gear, and outputs the right-hand side. So a parallel design is great. It's somewhat limited in terms of the torque that can be put through it. I'm going to go clockwise in fashion here between the different designs. The next one is a bevel gear. And as you can see, if I input to the pinion that is rotating the bevel gear itself, it's actually creating a right angle effect. So that spinning gear would be going in a direction 90 degrees to the input. So it literally causes you to input in one orientation and output in another. The same thing stands for the worm gear. The bronze gear on the bottom is actually going to be spun with an input to the pinion itself. With a planetary design, as we go farther forward, that's much different. So I've got a combination of gears being used. The center one, which you'll see some animation of here very soon, is actually what is brought into the input. That center or sun gear is spun, and the reciprocating gears on the outside work themselves around a ring gear that's embedded into the design of the gearbox. So hows and whys of gearing usage. What gets me my best solution? Why do I want to use it? If we go through and we talk about a gearbox, really what it's done, it's encapsulated transmission with gearing and transformation of rotational movements. So you can see in the animation on the right-hand side, I've got one gear spinning. It's causing an effect of another gear to do something different. What we're really concerned about is the rotation speed. Most things are calculated in units of revolutions per minute. They don't have to be, but that's just a common practice. As you can see, a speedometer on the left-hand side, what is it doing? A lot of cars have these nowadays, correct? So it tells you how fast the engine's actually spinning. In our example, we've got 1900 RPMs, which isn't really all that high. You can see on the right-hand side, if I get into the red section, I'm probably going to cause damage to my engine. In a more personal perspective, what does our globe do, our Earth? It rotates once per day, so it's basically 1/24th of an RPM. If I continue on and we get to a gearbox, the 3000 RPMs, if it's moving that fast in 2 minutes, it's basically a simple equation. I've got 1500 as an end result for the RPMs because it's a 2-to-1 match. So these animations give us a good idea of why the gears have teeth. So it's a more direct, positive fitting transmission of the movements and the torques. There are people that use in automation actually wheels. So they might be something covered with a rubber or some other type of material, or they could be just a metal wheel by itself. What happens in that case, though, is you can have slippage. You're not going to get that with a gear tooth. So as you can see on the left and on the right, they're fully engaged tooth to tooth, which provides a very, very positive contact. If I were to be utilizing, say, an overhead gantry, and I had simply a wheel moving on a piece of iron, there is a tendency where it could cause a slippage in that, and then I would not be positioned correctly. So gear pretty much prevents that. How planetary gearing works. So again, this is probably the most common type of gearing that we work with customers on. And there's several different types, but when we start talking about single stage, dual stage, and others, it really boils down to this. If you look on the left-hand side, there is this same sun gear, as I mentioned before, which is an input. It's making contact with 3 other planets that all rotate around a fixed housing which has the ring gear in it. So as I spin in, I say, a clockwise fashion, the sun gear or the pinion input, that planet carrier will rotate at the ratio that the gearbox was designed for. When I start looking at 2-stage designs, typically a single stage is up to about 10 to 1. If I look at something that's higher, and there's reasons why we might do that, to utilize a higher speed motor, because now with automation, we're not talking about windmills, we're talking about we have electricity, right? So if I go to a double stage gearbox, excuse me, phone just will not stop. If I go to a 2-stage design, I'm then coupling the planet carrier of the output of the first stage to the pinion input of the second stage. That is how you get the multiplication. So moving forward, product selections change by gear ratios. What does that do for us? Well, a couple of things. One, it changes the output speed, and that could be a good thing or a bad thing. 2, it can change the inertia ratio. And what does that mean for us? Well, if I'm changing the ratio and I'm inputting so much torque into it, we'll call it 10 Newton meters, for example, and I go from a 3 to 1 to a 5 to 1, I'm now outputting as a direct result 50 Newton meters instead of 30. But I'm also moving at a slower rate. That's item number 2. So my speed has gone down by 3/5 of the input. So instead of going, say, 300 RPMs, I may be going 200 RPMs. So it's going to offset the speed at which the output shaft actually moves. But my higher inertial ratio does another good thing for me. The motor that we have sized for a particular application has to emulate what the load is actually providing to the output shaft. And by that I mean, if I have a motor that has an inertia that's very low, and I have a load that has an inertia that's very high, that mismatch will cause instability in the operation of that system. We don't want that. So what we do is we try to get the inertia mismatch down to an appreciable level, typically less than 10 to 1 from the load side, from the input side. This also allows higher tilting forces in the output shaft of the gearbox, and I can change direction. So plenty of good things that come about when I'm changing the ratios of the gearbox. I can then manipulate the application to my liking. That may cause a change in price. You'll see it in the example that we talk about that in just a little bit, and how that can affect what the customer chooses. So continuing on, again, the main task for a planetary gearbox is to transform the torques that are needed for a particular process, whether it be drilling or moving. There's plenty of different applications that come up, but the ratios that are greater than 0 will make the output turn in the same direction. The ratios that are actually less than 0 will have an opposite effect. They will go in the opposite direction. This translation is important to know which direction I need my application to move. There's plenty of scenarios where we're talking about gantries or robotics, and I need to make sure that I'm going in the proper direction. Otherwise, bad things can happen. So I have a little bit of an animation that I showed earlier, but it was static. So again, the center sun gear has 3 planet gears rotating around it, and they're captured by the ring gear. What that sun gear will do, if I use an example of 10 RPMs in, and I'm at a 3:1 ratio, my gearbox output, that planet carrier connection, is only going to be moving a third of that. The next 2 slides actually talk about motor connections and what those are going to provide as an output. So you can see a motor, we talked about this inertia ratio, the JL over JM, and the torque being outputted by a particular motor. Well, we might be able to make that motor smaller if we utilize more of its speed range. If it's got a higher speed range capability, we can drive a gearbox appropriately sized, utilizing that higher ratio, which then brings down the inertia mismatch. But we often have to look out for other things, whether it gets the gearbox bigger, then we might have a mountability or footprint issue. We also might have to look at some other types of shaft bearings. If I'm going faster, I need to have my input be able to accept that faster speed from the motor. It's not always a tried and true method. Sometimes there needs to be several swipes at to make sure it's the right thing. Again, for our customers, they're always wanting to make sure we're optimizing. That's the main word here, is optimizing the application. And in this particular discussion, we're talking about planetary gearboxes and their ratios. A cutaway of a planetary gearbox, this is pretty much a standard. We've got the clamping hub that's going to attach to the motor input shaft, motor output shaft. So that's an important point. We don't want any slipping going on there. Also, we talked about the speed at which that motor can actually put into the gearbox input. The input bearings have to be selected for that operation. If I have a lower cost bearing that can actually meet those speeds, there's a purpose for it if it's more of a power transmission device, but I always want to make sure that the input bearings can withstand, say, a 4,000 or 5,000 RPM servo motor versus only an 1,800 RPM, maybe induction motor. As you can see, this is all encapsulated, as I mentioned before, with the housing. And these other bullet points on the right-hand side, and talking the blue and speed and green shaft loads, have to do with how they're applicable in the looking into the gearbox itself. So lubrication, that's important, because obviously if I've got grease or I've got oil, it's going to change typically how highly rated the speed of the gearbox may be. When I talk about output bearings, again, same thing. Well, almost the same thing. It's not an input bearing, but it's output bearing. But there are forces that are going to be applied to that shaft, or could potentially to that shaft, which may need me to increase the load capability of those output bearings. Seals have drag on them. You can see that in blue. So would that decrease the overall speed capability? It could possibly do that. Last but not least, we talked about the output and the shaft. So there can be different diameters of shafts that will provide more torque throughput in the gearbox. All of these kind of encompass just the cutaway of the planetary gearbox as it sits here on this page. And we're going to go to the very last couple of slides here. So I'm showing you a couple of right angle designs. And what does that do for me? Well, one, the advantages are I can now turn that device. If that motor could no longer fit into the machinery that I'm trying to automate the way it sits, but I can do it in a a vertical fashion, a right angle gearbox makes a lot of sense. They're also quite space saving these days. However, they're a little bit more expensive. So again, it's always the tried and true method of looking to see what the customer's expectations are, what specifications they've got to try and hit that sweet spot of what they're looking for. Last but not least, an example of changing gear ratios and a combination of what that changes for hardware that can kind of hit home with our customers. In one example, the customer proposed a solution of using a 10-to-1 gearbox and a 7.4-inch pinion. That's their setup for their mechanics. As we break down what those particular components cost, you can see that, hey, look, it even matters to the drive and the cables and the circuit breaker because I'm using probably a larger motor. This VPL B1654 that you see on the right-hand side is a fairly stout gearbox. It's a 165 millimeter frame, 165 millimeter frame motor. I apologize. And because of that, I'm having to utilize a bigger gearbox that can maintain the torque being put through it from that particular motor with only a 10-to-1 gearbox. What we change up if we look at this with Motion Analyzer is the fact that, hey, I can propose something different. I can propose a 25-to-1 gearbox, which means that that motor is going to be running faster, but it can still maintain that. However, that changes my pinion diameter, and then I start looking at the cost of those associated components, the pinion, the gearbox, the motor, and the circuit breakers, and I start seeing a reduction in cost. Many of our customers are looking for these nooks and crannies that they can save money on. And literally, if it's meant to be, and we can prove it with these sizing tools that we use day in and day out, then typically the customer's agreeable that, hey, look, I'll go ahead and select that based on your expertise. So that was the example I wanted to use just to make sure that everyone understood what we can do in changing up gear ratios and some of the components to offer up maybe a better opportunity or a better solution to the customer's requirements. That is pretty much the extent of my presentation today. I'm going to let Rachel chime in and see if we've got any questions from anyone.
Great, thank you, Gary. We don't have any questions at this time, but I'll give us just a moment here for anyone that might have some follow-up questions. And while we wait, I will just like to remind you, you can always reach us at the email address from the beginning of the presentation, macandmaclive@mc-mc.com, especially if you are watching this as a recording and you have any questions for Gary. Feel free to send us an email at that email address and just let us know which session you attended so that we can get your questions to him. All right, I do not see any follow-up questions yet. I want to thank you, Gary, for a wonderful presentation here today, and thank you to Tom for being our resource out in the comments section. Remember to subscribe to the McNaughton-McKay YouTube channel for more industry content, and we look forward to seeing you live again soon. Thank you, everyone, for attending. Have a great day.
Thank you, Rachel. Thank you.